Hello to viewers, welcome to my channel Science Technology. In today's show, Computer Wednesday, we're going to talk about computer translation layer. So let's dive deep into it. So what exactly is the problem? Well, problem is even though you could have a very latest and greatest software development kit or software SDK or instruction set architecture or operating system, they generally have a legacy that is ancient, like genuinely ancient, my 1970s kind of ancient. So that creates a problem, meaning even though you have a lot of tools, a lot of languages, a lot of this and a lot of that, all of them have ludicrously old legacy that they are supporting backwards compatibility wise, and penalty of that is they are very ludicrously bloated. Like they are like so much of the horsepower, so much of the microcode is just for backwards compatibility. It's not used anymore. It's just that they have to have it for backwards compatibility. So that creates a scenario. And be mindful, backwards compatibility used to matter a lot, but it became a self-fulfilling prophecy. Basically, imagine if you are in 1970, you made a system. You, of course, you will do your best that any system made in 1980s can support everything backwards. Okay, cool, awesome. But here's the deal. What about 1990s? What about 2010? And then you realize like, okay, now everything has to do backwards compatible from going back to 1970. So that created a scenario where the older systems and old conventions of programming of everything is basically limited. And all that limitation that we used to have, like for example, very common example is when x86 was built by Intel, they utilize a philosophy known as complex instruction set architecture, meaning one call will do multiple tasks. Now sounds great, then question becomes why? Well, they wanted to do this simply because back in those days, RAMs were ludicrously expensive. RAM is free right now. Like you could literally have 12 gigabytes of RAM in your computer right now, in your smartphone right now. Heck, you could have 2 to 3 gigabytes in your smartwatch. Nobody cares. RAM is dirt poor. Now that CISC architecture was made in a world where 128 megabyte was unimaginable. Whereas like, you are telling me you can have 128 megabytes of RAM? Whoa. So they designed the system best for that. But again, similarly, at that time, ARM Corporation, they took a different gamble. They were like, okay, what if we use RISC? RISC is reduced integer, meaning one call does one thing: call memory, load memory, do compute, dump memory. So everything is there. So that CISC architecture did work in 70s, did make Intel the daddy of the world. But over time, it started to reach a point where, as of now, meaning if you look into any modern i7 series processor, i9 or whatever have you, open it up, you'll find there is a translation engine on a silicon level that is just translating ancient codes to run modern RISC-like system. Translation engine on silicon. Because again, the growth of calculations that we can do right now, it's unimaginable. Basically, it goes like last 10 years, we have seen more growth than like previous 50 years, so to say. So it's bonkersly fast at this point in time. So there is a problem. It's like if we are still using the philosophy, the architecture, the everything else of the past, the bloat becomes a hurdle itself. We are unable to utilize the horsepower that we have right now. So question becomes, why translation layer becoming a tool right now? People must have thought about it. And yes, like gaming consoles always had this idea like you should be able to play PlayStation 1 game in PlayStation 2, should be able to play PlayStation 2 games in PlayStation 3. This sort of idea was there, even with Nintendo Wii. But in computer, things changed. The specific thing is, compute became a part of our daily life, meaning right now, any child is born generally will have a smartphone. And reality of is, everything, like your bank ATMs to your satellite entertainment to every Tom, Dick and Harry thing requires compute, bonkers amount of compute. So that creates a financially rich environment. That creates a lot of competition. And because you have a lot of competition, things move fast and ever faster. Like basically the growth that we are seeing in last 15 years is like, holy damn, like 15 years is just barely enough. Where it's like when I was in institute, smartphones were becoming a thing. That time they were like 512 megabytes of RAM. Whoa. 2 megapixel picture. Whoa. Now it's like, bro, I don't even care. So fundamentally, so how can we reach that? What is the fundamental limitation? Now, like, okay, what if we put more power, we get more compute out of it? Yes and no. Yes, that was the thing that x86 tried to do, but ARM took it in a different way. And again, fundamentally, people realize inherently you are limited by compute for power, meaning you want to do as much compute as possible for as little power as possible. And it affects both, not only your smartphone, because people can say, oh, smartphone, battery limited. Does it matter to server? Absolutely, because if you can do a lot of compute for a lot little power, you can do a lot more. Let's say you have a power budget of 2 gigawatt, right? You get a 2 gigawatt system. That's a power limitation, 2 gigawatt. You cannot draw more than that. If you are efficient with that 2 gigawatt, then you can do a lot of compute. If you're not, you can't. So that's why everybody realized very early on is that the current frontier is compute for less power. It does not matter whether it's for a microcontroller, does not matter it's for a mobile phone, or does not matter it's a supercomputer of AI computer or something like that. Power efficiency is the key. Now, you can't reach those efficiency if the foundation is corrupted or if the foundation is inefficient. Why foundation is inefficient? It was not designed with modern hardware. The foundation is ancient. It's like, what if in 1970 we designed something and we kept forcing to use it? It's like, yeah, we are doing it. Sort of. So fundamentally, the foundation is not efficient. So that creates what we call bottleneck. No matter how fast you make your basically stuff, like it's like saying, oh, people want to use Python, then look into it, it's like C++ inside the basically library and all that, similar thing. So fundamentally, everybody reached a bottleneck. Same place is that we cannot use these older systems. We have to start new. A blank check. We have to, because our growth of hardware is bonkersly fast. Like in 1999, AMD became the first company for civilian use to reach 1 gigahertz. Just few years later, FX series cracked 5 gigahertz. Right now I have a system, and now again that required a lot of cooling, and I think liquid nitrogen was needed. But right now I have a computer that can easily reach 5 gigahertz if I mildly overclock it, mildly. But again, it already runs at like 4.8 most of the time. So the growth, basically we went from kilohertz, whoa, to megahertz, whoa, to gigahertz. And all of this happened very quickly. Like this side is logarithmic. That's how fast we climbed. So people realized that modern hardware is fast enough, meaning at this point in time, you can run the translation layer that utilizes the modern hardware, the modern architecture, modern way of thinking to do the same task. And you can maintain compatibility without slowing down the whole system. So, and again, that also gives you flexibility where it's like, hey, I need this for this hardware. Ta-da, make your own silicon. You're no longer limited to ancient x86. So this is why right now the market is hot for translation layer. Now let's talk about the most popular translation layer, Rosetta 2. Now, before you understand Rosetta 2, you have to understand Rosetta 1. Now, Apple is a company that ditches its past like there is no past. So Rosetta 1 was translation layer made in 2006 because they were basically getting divorced from basically Motorola, and they were getting married to Intel. And they wanted some way of dumping all the software libraries into x86 without stopping the system. So they created Rosetta, dynamic binary translation, run existing apps, transparent to user, lightweight, fast enough. Now again, this was their first attempt. It was not smooth sailing, but again, you have to understand 2006 market was completely different versus right now. So they did do that, and this was their lot of learning experience happened, and they always created a 5-year time buffer, meaning Rosetta 1 was never meant to run for long. It was just like, we change, this is a buffer time, change everything, by the 6th year we're gonna shut this down. So Rosetta 1 was kaput after 5 years. Then Rosetta 2 was created. Why? Again, another divorce. Basically, they got divorced from x86. They created their own ARM silicon system. So they're like, okay, now we have to port. Now, how it's working? Well, again, they have learned a lot from their past experiences. So this time they have a dual prong attack. First is binaries are translated once if it is important. Basically, let's say you are running a Photoshop. Photoshop will have certain calls, like let's say viewport. It has to run that system. So that system translation would be done and then put into cache. But it will have a lot of other smaller calls like filters, blur effect, this and all. Those will be there, but they will not be cached, because again, cache is a limited system. So you want to use it wisely. So the core application gets translated, it dumps into the cache AOT system, and then you have translation on the fly, meaning if you open a drop down menu for filters, then it's like, whoa, each person is in, then it translates that. Now, it works, and because again, this was attempt 2, Mark 1 is always garbage, this was genuinely smooth. It was like, they can actually port enough things. They can port even Adobe and all that. Now, let us figure, Apple burns the past. Like, there is no bridge to the past in Apple. Apple is like, there is no past. We are only future. So they had a very simple dialogue with every software developer. It's like, bro, 5 years, port your damn system. After 5 years, we're gonna kaput the system. I'm like, wait a minute, that's 5 years right now. Yeah, they kaputted it. So at this point in time, some applications are still hanging on, basically games, and they are saying that we, for certain use case, they might maintain a very limited use case, so to say, for gaming. But again, it's not likely. Again, even Valve is not interested into that, because again, there's not that many gamers on Macs. And it's like, if you have to go through that much hassle, it's like Valve is like, wouldn't it be cheaper if I made my own operating system? So that's why Rosetta 2 is like now reaching the tone down period. Some what you call skeleton crew might maintain it for games and all that, but don't expect too much about it. And while other things have been ported, like Adobe Suites and all that jazz, but many things have not been ported. Those will get kaput. So that is Rosetta 2. Now we come to the magic that should not be possible. That is Proton layer. Now Proton is basically the idea Gabe Newell had is like, we love the library of Windows. There is no games library that even comes close to Windows. Like if you think, oh, consoles have this and that, no. Like there are zeros missing. If you put all the consoles, be it Nintendo, be it PlayStation, be it Sony, put all of them in one side, PC would be like, bruh, like there are zeros missing. And the exclusives, even those are not that what you call ironclad as they used to be. You can play legally God of War right now in your system. Yeah, you can't do much with basically Nintendo, but even Nintendo, some of the licenses are available. So Valve looks into it. It's like, what if I made my own operating system that was better? Because while Windows library is awesome, the Windows operating system is kaput. It's poo-poo. So they're like, okay, we want to run Windows game. That's the core part. We want to run it on Linux. There was an open source ecosystem for that. That was called Wine, Windows emulation. So they took that Wine, created a fork of it. That fork is Proton. And the idea is go on to base level and basically replace all the Windows API calls with Unix-based system, meaning act as a translator, meaning Hindi is coming in, English is going out, English is coming in, Hindi is going out. So act as a translation layer. So they have a lot of translation layer. One of the code translators that makes sure the past library can be maintained, that is DirectX 9, DirectX 10, DirectX 11. DirectX is a Microsoft product that basically talks, is like a low-level API that talks to the hardware, like the GPU. This is the puppy that talks with the game engine and the GPU. That's the layer. So they're like, okay, they have a system that translates all those older DirectX 9, 10, 11 to Vulkan. Vulkan is a completely different system. And then you have a upgraded version of that, that is VKD 3D. That 3D is Proton's direct conversion for DirectX 12. Because DirectX 12 is far more recent, they does require a bit more oomph for that. So DirectX 12 would be converted into Vulkan API calls, meaning Hindi comes in, English goes out, English comes in, Hindi goes out. So game does not know. Like from a game's point of view, game does not know whether it's running on Linux or Windows. Only anti-cheat software goes deep enough into the system where it triggers some alert. In most other scenarios, game does not know. It's like I'm running in a virtual sort of app. There is an app translation layer. And audio, they have to use, basically Microsoft has a protocol known as X audio system. And they changed the X audio system to F audio system. Awesome name. So what they managed to do is miracle, because in last 2 years, they somehow made sure the basically SteamOS. Basically, you can buy it on other hardware. So it's not, oh, Steam optimized. No. You can buy it on other hardware, basically ASUS ROG system, and you can play Windows game on that. And you can play Windows game if you install Windows itself, and both are x86, it's not ARM. So x86 hardware running Windows, trying to play Windows game is a worse experience than running SteamOS, having a translation layer, and utilizing Windows games. Is like, how the heck that happened? Like, and that is why the Apple translation layer is like, okay, A, they already had experience. B, they burned the past. Valve is like, bro, we have nothing. Like in terms of people, like I'm telling you, if you compare the Apple size to Valve size, it would be like they would have more sweepers. Like Apple would have more sweepers than programmers that Valve has. Like that is the scale difference. And somehow Valve is like, let me port the world's biggest library. Damn. So they did manage to port it. And again, in 2 years, like you can check every single reviewer. It's like, yeah, I could see it, but it's not that good to right now. Bro, don't deal with Windows, man. This is the gaming. So 2 years. That's called polish. So that's the whole magic of Proton. And again, I have said it time and again, Linux does not matter unless somebody puts some money into it. And Valve is like, allow me. So in 2 years, they managed to do something unimaginable. So this is the best example, because how few people managed to do this. And yes, they utilize open source community, but here's the open source community, meaning Apple could have also done that. They did not. Nobody could have done that. And Valve is like, allow me. Now we come to the big puppies. So AWS. Now AWS right now is no longer the daddy that it used to be, but there was a time in the early years where Amazon Web Service was the internet. Meaning if AWS just got poofed, entire internet will go poof, kaput. Right now it's much better. Right now we have a lot of share in Google. We have a lot of share in Microsoft Azure, and a lot of in AWS. So that's much better, healthier ecosystem. But there was a time for a few years, AWS was like, that's why Jeff Bezos is so rich. So what is AWS? In simplest term, AWS is a company that builds the hardware, like physical silicon, the cabinet, the water cooling and all that jazz. They build the goddamn hardware and then they virtualize it. And they have their own hardware, they virtualize it, and then they sell the compute on those virtual environment. And benefit of that is it's very easy to tailor-made, meaning they're like, hey, we have, like, let's say unit, and they can separate the unit based on requirement. For example, for Netflix, they're like, hey, port as much data for that, but they do not need too much compute. Try to port as many compute hardware that is dedicated for transcoding. And they're like, okay, this company is running some database servers. You maximize the RAM uses there. You don't need to worry about SSDs and basically main storage. Make sure the RAM is allocated. So because they are on a virtual layer, they take care of it. And because they have an ability to collapse everything into one virtual pool, they are very resilient. And again, they give you very headache-free experience. As people say, I do not know how headache-free it is, but people say that's why people pay for AWS. It's headache-free. Comparatively, let that be very clear, comparatively. So the benefit AWS had is that they had complete control over the whole system stack, meaning because they were running on a virtual system, the hardware was their own. And again, they had switched from older hardware to newer hardware, and every time there was some growing pains, and they did manage it. So they also had certain experiences like, hey, we can deal with this. So they have complete control of the hardware level to operating system. Now, again, the operating system here is different compared to operating system you and I use, but it was still there and Amazon controlled it. And then they built their own in-house tools that allowed them to port everything to their own silicon. They basically went from like, hey, why pay basically Microsoft, why pay Intel for x86 license if we can make our own? And because we are the biggest customer there is, relatively speaking, they're like, we know what we want. Why we have to, like, deal with the generic component that Intel is giving? What if we designed what we need? So they went to ARM, got the license, they built their own silicon, brick by brick, day by day. This is silicon number 4. So they actually managed to crack it. They actually managed to port everything without breaking backwards compatibility. Because again, if you know anything about servers, you must understand the fact that the ideal server uses is 100%. You try to use 100% of it. So they managed to do that and make sure it does not break, because again, these customers have the ability to sue Amazon into oblivion. So they're like, yeah, we have to make sure that it's compatible, it works, thing is very resilient and backwards compatible. And all of that was done methodically, brick by brick, day by day. And now Amazon is like, what Intel? What is this thing you talk about Intel? Basically, they had optimized libraries, software development kit, and they also had guides. And this is their library where people are actually looking into the symbols and all. Do not Google the price of this sort of oscilloscope. Ferrari will look cheap. Not even joking. So basically, they built their own ecosystem, own hardware, and their future plan is, which again, let that be clear, because Amazon Web Service was such a big deal, and the fact that it successfully managed to do it without having a catastrophic failure, Microsoft is like, hey, why pay Intel? What if we make our own silicon? They made their own silicon. Meta looks at it like, hey, why pay Intel if you can make your own silicon? So every company is making their own silicon. And because of development of translation layer and the fact that modern hardware is so goddamn fast, and this was like the big jump where it's like, whoa, 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 you can do that? On a server level? On a 24/7 into 365 into 5 years hardware? Yeah. So everybody is jumping right now. And the end goal is jump from ARM also. Basically, why pay the license to ARM when you are designing all the thing? Jump to RISC-V and look into RISC-V's, basically who are the big contributors to that. So I can easily see in the future where large companies simply means they have everything their own. Basically, they have their RISC-V system, they have their own software stack, they have their own hardware, everything is their own. They're like, why give money to something else? So this was my presentation on basically the ecosystem of computer translation layer. Hopefully you have liked it, learned from it. In that case, please give the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe Press the bell icon if you're free, and as always, thanks for watching.